Okay, so happy Friday, everybody. Completing our first week here. Just 9 more to go, and I guess 2 more quarters after that. So, okay, so we are still in. We're talking about Bayesian inference, and the example that we've been running with is kind of our baseball example. Baseball batting averages. And we said the prior distribution can be said to be beta 81 to 19, which ends up looking something like this, where we kind of get a peak at around it's hard to draw, but you know, we have a peak, kind of the mean is going to be around 0.27. Okay. And what this the PDF of the beta of beta 81 to 19 is we'll write f of x is equal to 1 over b 81 to 19, which is some crazy number, x to the 81 minus 1 times 1 minus x to the 219 minus 1. Okay. Our data comes from, you know, we can either call it a Bernoulli or a binomial, and the difference there is that the Bernoulli is kind of going to like a sequence of Bernoulli trials, an exact thing, and the binomial will have a kind of a factor that tells you how many combinations we have. Okay, and so if we have let's say 5 hits and 5 outs for a total of 10 at-bats, then the likelihood is going to be x to the 5, where I'm going to let x equal the probability of a hit, which is basically the same thing as a batting average. Okay. I mean, there's a subtle difference there, but just for the simplicity of our thing, we're going to say the likelihood of getting this data is going to be x to the 5 times 1 minus x to the 10 minus 5, which is also 5. And when we do, when we use Bayes' rule, okay, the posterior distribution, which is what is the probability of, so we can say this is, what's the probability of basically the parameter given the data. We say this is going to be proportional to the likelihood times the prior. All right, and so the likelihood here is the probability of getting our data given the batting average x times the prior distribution, which is going to be our beta. Okay, and so when we combine this, we have the likelihood, which is x to the 5th times 1 minus x to the 10 minus 5, and we're going to multiply that by the prior, which is, you know, 1 over b81 to 19 times x to the 81 minus 1 times 1 minus x to the 219 minus 1. Okay, so this is should all be review from what we did on Wednesday. Okay, so I think I did all of this stuff on Wednesday. Let's see. This is stats 102C 1-3. Okay. All right. Is everything so far so good? Any questions about where any of this stuff is coming from? Okay. And so when we have this likelihood and we multiply it by this prior distribution, the results combine nicely, okay? So we have x to the 5th, 1 minus x to the 10 minus 5, which is 5. And then I'm going to move that constant 1 over b 81, 219. And some other constant, x to the 81 minus 1, 1 minus x to the 219 minus 1. And this combines nicely. And then I'm going to just write constant times basically x to the 86 minus 1 and 1 minus x to the 224 minus 1. Okay? And we say, well, that looks very much like a beta distribution with parameters 86, 224. Beta distribution with parameters 86, 224 is going to be b86, 224, x to the 86 minus 1, and 1 minus x to the 224 minus 1. And we know that this thing has to be a probability distribution which integrates to 1, and this is the only thing that's going to have this form that also integrates to 1. So the result must be this beta distribution, 86, 224. And so, you know, the fact that the beta distribution combines nicely with the likelihood of a sequence of Bernoullis. A sequence of Bernoulli outcomes. Okay, and so when you have the prior distribution multiplies nicely with the likelihood, that prior distribution is called a conjugate prior of the likelihood. Okay, so not all distributions have this nice property where when I took the likelihood and I took the prior distribution and I multiply them, they combine nicely. Okay, but there's a family, or there's a bunch of let me think how to say this. For many likelihood functions, whether that be the Bernoulli, the binomial, the normal distribution, the exponential distribution, for many probability likelihood functions, many of them have what they call a conjugate prior, a prior distribution that if you use it will combine nicely. Okay, so a conjugate prior is a probability distribution that has the kind of property that when multiplied by the likelihood, multiplied by its corresponding likelihood, the terms combine nicely. Okay, now nicely is a relative term in that, you know, you might have to do quite a bit of algebraic work in order to kind of reform all of these things, but they do combine nicely. And so I've just I posted your first homework assignment yesterday, and I don't know if any of you took a look, but you'll have a series of problems dealing with likelihoods and their conjugate priors, and you're going to have to do some math to kind of combine these things, okay? So, you know, if I go to Wikipedia, I can type in conjugate prior, okay, and then Wikipedia will have kind of a list of distributions that are conjugate priors, okay? And so this is basically what we see, you know, here's your, this is Bayes' rule. This is the distribution of the parameter given the data x is the likelihood, the data given the parameter multiplied by the prior distribution of the parameter, okay? They've got a few examples, but here we see the Bernoulli likelihood combines with the beta distribution as the prior, okay? So if our data comes from the Bernoulli distribution, which is what we have in this baseball situation where either the outcome is a successful hit or a failure, which would be an out, the corresponding prior distribution or conjugate prior is the beta distribution, okay? And what we see is that they actually already give you the answers here. The posterior hyperparameters, meaning that after you combine, if your shape parameters are A, alpha, and beta, okay, the result, when we went from 81 to 19 and we had 5 hits and 5 misses, the result was 86 and 224. It's saying that the resulting shape parameters will be, you know, basically that 81 plus the sum of the successes, okay? So that's 81 plus 5 gives us 86. And this also shows us that the other parameter, the 219, is going to be 219 plus n, which was a total of 10 observations minus 5. So 219 plus 10 minus 5, which gives us 224, okay? And so, you know, the math that we did similarly lines up with what we observed, or what we calculated here. And let me just go ahead and I'll just copy this into our notes. So this is from Wikipedia, and what we have here is we had 81 and 219, and then the sum of x is 5 and n is 10, and so you have 81 plus 5 is equal to 86, and indeed we have 219 plus 10 minus 5 is 224, and that's how that's what we found ourselves. Okay. All right, so let me, we'll do like another example here, okay? So perhaps, I guess we can do something like the, what is one that I'll want to do? Okay, we'll go with the exponential, okay? The exponential distribution. All right, so we'll say the data come from an exponential distribution. Okay, when do we use an exponential distribution? Exponential distribution can be used to model waiting times, right? The amount of time between random events, right? Used to model waiting times, or basically the time between random events. Okay, so let's say we want to model the time between, do you guys ever eat on campus?
Yep.
Okay, all right. So who's like, what do you think is like the busiest eatery at Ackerman? All right. Okay, let's go with Panda Express. Okay. All right. So we'll say we want to model the time between customer arrivals at Panda Express. At noon. Okay. So that's like peak lunchtime. All right. How long do you think? Like somebody gets in line, and how long do you think before the next person gets in line? So you think a customer arrives every 5 seconds?
30 seconds.
I think it's longer than 5 seconds. 5 seconds is a lot. Okay. I don't know. All right. Okay. Maybe we should go. All right. So I guess our prior, okay, kind of our prior feeling, all right, is that I guess wait time between customers. So if you had to give me a range, what do you think it's going to be? Huh? Between what? Between 60 and 90 seconds?
5 seconds to 1 minute.
Okay. All right. So our prior feeling is that the wait time between customers is, we'll say between, I don't know, we'll say 10 seconds and 90 seconds. Okay. So that's kind of a wide range of values. Okay. And so what is in the exponential distribution? Which the PDF is this. It's going to be lambda e to the negative lambda x. Okay. Okay. The lambda represents what? The lambda is the rate parameter, right? Okay. So what we are saying is that our prior feeling is that our rate is somewhere between lambda equals 6 and 90. What's the inverse? Like six arrivals per minute. And if it's every 90 seconds, then we've got, what's that? 2/3 of an arrival? Okay. The rate is equal to 2/3. Okay. Something like that. 2/3 of an arrival per minute. Okay. So this is what we have. So our exponential distribution needs some kind of, we have to plug in some kind of rate parameter. Okay, so we're going to try to model the number of arrivals per minute, and we are saying there's somewhere between 2/3 of an arrival and 6 arrivals in 1 minute. That's a pretty wide range, okay? But at least we know it's not going to be like 1/10 of arrival, okay, where it's like 0.1 of a customer, like one customer shows up every 10 minutes. We know it's not that long between arrivals. And we also know that it's not going to be much more than like 20 arrivals in a 60-second span or something, okay? Okay, so we can model something like this. This can be modeled if we look at what the conjugate prior is. The conjugate prior can be modeled with the gamma distribution, okay? The gamma distribution is, it's a little bit of a weird thing, okay? It can be used to model wait times, except it's going to be kind of wait times using, you have two things. You got a shape and a rate parameter, okay, or a scale parameter. And it's kind of the idea of, so if the exponential is how much time between this event and the next event, the gamma can be used how much time between this event and 3 events from now, or something like that, okay? So the exponential is how much time until this light bulb breaks, okay? Right, so I think like light bulbs are classic exponential distributions, okay? And then the gamma could be like how much time until we observe 5 light bulbs breaking or something like that. Okay, so the gamma distribution, and so we might have to just do a little bit of kind of guess and check here, because maybe we don't have the most comfort with the gamma distribution, but we'll just pick some arbitrary values for coming up with our prior distribution. Okay, so I'm going to have I forget how is so we're going to check how gamma is parameterized in R, okay? And it says we've got the shape and the rate, okay? So I'm going to go ahead and I'm going to just call shape something. We'll start off with 1, and then we'll say rate is equal to, I don't know, 4, okay? And I'm just starting off kind of here, and we're going to create a sequence from, say, 0 to 20, and we'll go by equals 0.1, and then our density, I'll just call this D, will be D gamma of the values in our sequence using shape equals shape and rate equals rate. All right, and then I'll go ahead and I'll plot S versus the density, type equals L. Let me just call title will be paste 0, gamma with shape equal to shape and rate equal to rate. So we'll do type and main equals title. Oops. All right. So we'll go ahead and try this. Okay. So this is here I've got exponential, basically an exponential distribution when shape is 1. So we'll try like shape 4. Okay. And okay. So now we're seeing what we want is kind of the value that we get here to be somewhere between 2/3 and wait, where did I write this? We want it to be somewhere between 2/3 and 6. Okay, so we can kind of, so as you discover something like this. Okay, so now we're positioned a lot higher, and you can also just kind of see what effect changing the shape does, right? So if I go 20 and I go up to 50, it shifts the whole thing up, right? And so what ends up happening is that kind of the mean, the central value ends up being the ratio between the shape and the rate, okay? So maybe I want this centered around 3. So I might do something like 10/3, okay? And that looks to be centered closely, and maybe we can see what effect we have. If I reduce this to 1 and 0.3, well, that doesn't work quite that well, but 2 and let's say 0.6, okay, we can see there's a more spread, and as I increase this to say 3 and 1, the amount of spread kind of shrinks, and as I go up to kind of 10 and 3, it does that. And if I do 30 and 10, it gets more narrow, okay? And so there's kind of an idea of, so, you know, it's a little bit arbitrary, all right? A little bit, right? But we're kind of just using our prior experience and what we're thinking, like, how many customers do we think arrive every minute at the Panda Express line, right? And we think something between 2/3 of a customer and 6 customers arrive every single minute when we're, you know, kind of just looking at how long it goes. Actually, here, let's see. Let's think of what a good estimate would be. How long does it take to get through the Panda Express line? Like once you stand in line, how long until you check out? Probably like 6-7 minutes, something around there. It's like you gotta wait, but it's not like super crazy long, okay? And how many people do you think are standing in that line, if you counted them all? 20 to 30. Okay, so we got 20 to 30, and it takes you 6 minutes to get through the line, 7 minutes to get through the line. Okay, so that's probably, we should be centered around, like, if it's 30 divided by 7, you know, something around 4 minutes, something around there, 4 arrivals per minute or something like that. Okay, all right, let's just kind of ballpark this, all right? And I'm just making this up, okay? We're not quite sure what exactly it should be, but maybe we're going to have a gamma with a rate between 20 and 5. Okay, gamma with these parameters, 20 and 5, and maybe we can just zoom in a little bit closer to the sequence here. Okay, and so this is saying, you know, kind of the number of arrivals per minute is probably close to 4, maybe as high as 6, maybe as low as 2, probably not too much higher. Or if you disagree, you know, we can go 16 and 4, and this will add a little bit more spread. Okay, and this does that. Okay, so maybe we'll do this. Does that feel okay? There's a little bit of an arbitrary factor here, right? But this is kind of the notion in Bayesian statistics, right? We come in with prior knowledge so that just in case in our data, if we get something a little bit unusual, we're not just going to say, well, the data says the batting average should be 0.5, and we're just going to go with 0.5, right? But we're doing this in a little bit more of a controlled way, rather than saying the maximum likelihood estimate for batting average is 0.5, so we're going to go with that. We're going to say, you know what, let's kind of scale this in. But rather than just doing arbitrary and saying, well, 0.5 seems unreasonable, but 0.3 seems better, and just picking 0.3, we do it in a little bit more of a controlled way, and we can at least explain my prior beliefs were this, and this is how I ended up here. And so similarly, I can at least explain that my prior beliefs regarding the rate parameter of how long we're waiting at Panda Express is based on, I'm just kind of guessing about the line, but this, yeah, I don't know, as a classroom, maybe we seemed to sort of agree that this sounds reasonable. Okay, so I'm going to go ahead and I'm going to copy that. And so we'll just say, you know, with a bit of kind of guess and check, we decide on a prior distribution of, we're going to go gamma A equals, what was it? 16 and 4, or something like that. How is it parameterized here? Okay, sorry. Yeah, A is 16 and B is going to be 4. Okay. How do I copy this? I thought I did this. Okay, it's not working. Did I mess something up? Gamma A is 16 and B is 4, I think. So the mean is A over B. Yeah, I think that's right. Okay. Okay, so we start off here, and then we're going to go ahead and we'll say, okay, let's go out and gather some data, right? So you go to Panda Express, and you decide to time how long it takes between customers arriving. Okay. All right. So we go and we do data collection. All right, and so we're going to measure. So we're going to say. As soon as you get there, you start the timer, and then the first customer shows up 15 seconds later, right? So your wait time, so this is 15 seconds, and then so we recorded a wait time of a quarter minute. The next customer comes in 30 seconds later. Another customer comes in, I don't know. Okay, so we're gonna just kind of gather some stuff. Okay, well, yeah, let's, and let's do one more. How much does this add up to? I don't know. I can't add. Okay, 0.25, 0.5, 0.3. Huh? 1.05? Okay, so it adds up to 1.05. Okay, so this is what we have. All right, so we have 1.05 minutes total, and we saw 3 arrivals. Okay, and of course, I think we would agree that if we were to just have this short amount of span and then say, okay, well, this is then the arrival rate, this seems a little silly. But if we want to factor this in to our data, we can do this. Okay, so our likelihood, kind of the total likelihood, is going to be the product of our PDFs, right? So we're going to have basically lambda e to the negative lambda x, okay, for n equals 1 to 3. Okay, so I guess x sub n. All right, so we're going to have lambda e to the negative lambda times 0.25 times lambda e to the negative lambda times 0.5 and times lambda e to the negative lambda 0.3. I should indicate all of this like this. Okay, and so the total product, what's this total product going to be? It's going to be lambda cubed e to the negative, I guess, 1.05 lambda. Is that what we have? So this is my likelihood. All right. The prior distribution is gamma with A16 and B equal to 4, which is takes on this form. Okay, the gamma distribution has this PDF. It's got this scary stuff up front. Okay, so I mean, I'll go ahead and I'll write it. Okay, beta to the alpha, gamma of alpha. Gamma function of alpha. Okay, so that looks scary. And then x to the alpha minus 1, e to the negative beta x. Okay, so keep in mind the value that we are drawing from the gamma distribution. This produces what value? This is the prior distribution of our rate parameter. So the rate parameter lambda is drawn from the gamma. Okay, So we will replace x with lambda, because that's the value being drawn from the gamma distribution. So by default, when you go on Wikipedia and you look at PDFs, the value being drawn from that distribution is written as x, okay? And in this case, the value that we are drawing from the gamma distribution is our rate parameter, okay? So because we are saying that our rate parameter is going to be something between 2 and 6 here. We're saying somewhere between 2 and 6 customers arrive every minute. And so we're going to write lambda to the alpha minus 1 and e to the negative beta lambda, or I guess a, well, whatever. Okay. Sorry, I'm a little bit sloppy here. E to the negative beta lambda, okay? And so right now, with our prior values of 16 and 4, we've got 4 to the 16th divided by gamma 16. I don't know what that is. That's some crazy number, right? And then this is going to be lambda 16 minus 1 and e to the negative 4 lambda. All right, I will combine this with my likelihood, okay? So over here, the likelihood times the prior will give me something proportional to my posterior distribution, which is going to be the probability of lambda given the data that we've seen, right? So that's what we're going for. Okay, so the likelihood is lambda to the third, e to the negative 1.05 lambda. And then my prior is, I'm going to just kind of ignore the constant for now. And we've got lambda to the 16 minus 1, e to the negative 4 lambda, right? And so this combines and we get lambda to the 19 minus 1 and e to the negative 5.05 lambda. Is that all right? Okay. And can we get, can we find an alpha and a beta so that this thing is, kind of is proportional to a gamma distribution, right? So the thing is, we had gamma prior, we multiply it by our likelihood, and so this is basically equivalent to a gamma distribution with what? What are my shape parameters for my revised gamma distribution? It's going to be with A equal to 19 and B equal to 5.05. Is that okay? How I got these values? So we're just combining the likelihood and the prior to get kind of the resulting shape to look something like this, right? And so, so what this looks like is that maybe I can just add a line. I'm going to have 19 and 5.05, and let's just add this. Color equals red. Okay, so I'm going to go ahead and do this. Okay, so this is the prior distribution, and then after observing 3 more observations, the resulting distribution looks a little bit like this. Okay, where if we just did this right now, basically the MLE estimate would be that the wait time is 0.35, which corresponds to a rate of just a little bit under 3. Okay. And so rather than just saying, well, the answer is definitely 3, okay, it just reshapes kind of the resulting distribution to kind of shift a little bit closer to 3, okay? And as we observe more data points, okay, like let's say we observed, 100, instead of 3 arrivals, 30 arrivals, and they have this exact same pattern, right? So after 30 arrivals, we've waited 10.5 minutes, and we have 30 arrivals, and if we did that, I think our result would be, I would add 30 to 16, so I would have 46, and I would add 10.5 to 4, and I would get 14.5. And this will actually not fit anymore, so I'd have to okay, well, let me just do this part, okay? And so after observing 30 arrivals, kind of the resulting distribution is a lot closer, centered at 3, okay? So as we observe more data points, our resulting posterior distribution gets tighter and tighter, indicating kind of basically more confidence or more, a higher probability that it's located kind of centrally around our data point there. Is that right? And similarly, if we look at kind of this conjugate prior and look at the relationship between the exponential and the gamma, it says, the updated parameters that you'll see is that you take your prior value alpha, okay, which prior was 16, and you update it to be 16 plus the number of observations, 16 plus n, okay, and that's how we got 19. And then you take your beta, which in our prior was 4, and then you add to that the sum of your x values, which was 1.05, okay? And so that's how we got 5.05. Right? And so, this chart kind of gives you the answers for a lot of these things, okay? I do think it's worthwhile to kind of do some of these, the math yourself and figure out, see if you can arrive at the same kind of resulting kind of parameter selections, right? So in your homework, I have you do it for the normal distribution. The normal distribution is a little bit of a pain. You've got to do some algebraic manipulation to get things to work. But, I hesitate to say that you can do this, but at the end of the day, you can kind of compare your result to what is known and printed on Wikipedia. I would encourage you not to just jump there right away, though, okay? Because I might put something like this on an exam, and you won't have Wikipedia to save you then, okay? All right, so the next thing I want to have us start thinking about is how can we use our posterior distribution to start answering questions about kind of the results, right? So let's just kind of switch back to classical frequentist mode. Okay, so in classical frequentist mode, you get, you have your data, blah, 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 and then you estimate the maximum likelihood estimate of some parameter. Okay, so for example, in baseball, if we have 10 at-bats, 5 hits, our p hat, maximum likelihood estimate of p hat is going to be 0.5. All right, let's just sorry, let me just change this just ever so slightly so our thing becomes a little bit more, a little bit less 0.5-ish. Okay, so this is what we have, all right? And if I said, okay, based on your estimate, okay, what is the probability that the player will get 2 hits in the next 3 at-bats. Okay. So how would we go about answering this? This is just I want to say a simple problem, right? So what kind of distribution do we use here? That's just a binomial problem, right? N is equal to something, and P is equal to something, and what's the X that we're going for? What's the probability we get 2 hits out of the next 3 at-bats? Okay, so my number of trials is 3, and my X is 2, and what's the P? P is going to be my maximum likelihood estimate of 0.4, okay? Is that all right? Okay, and then so we would do N choose X, P to the X times 1 minus P to the N minus X, and we get 3 choose 2, 0.4 squared, 0.6 to the 1, and I don't know what this is, 3 times 0.16 times 0.6, 0.96 times 3, 2.84? Is that, no, 2.96, 2.88. No, that doesn't make sense. How's that even possible? 0.288. Sorry, thank you. Okay, so we get 0.288, and that's our resulting probability. Okay, that's okay, right? So that's classical, and this is easy. Classical frequent statistics is easy because there's only one value for p hat to plug in here, okay? Easy because there's only one p hat value. Okay, in the in Bayesian, however, okay, after our data, we do not have a single estimate, a single value estimate of p. What do we have? We have a probability distribution. Okay, so if our prior is beta 81, 219, and we have 4 hits, 6 misses, then our posterior is going to be beta, what, 85 and 225, okay? So that's what we have. And basically, our p can be any value, can technically be any value in, you know, whatever this thing looks like, okay? It says some values are more likely, okay? It says, you know, values around 0.2 whatever are a lot more likely. Values greater than 0.4 are very unlikely, but technically there's an infinite number of possibilities that p can be, okay? Okay, so how do we answer the question, what is the probability of getting 2 hits in the next 4 at-bats? Or in next 3 at-bats? Okay, so how do we go about answering something like that if we don't even know what p is? If p can be one of infinitely many values? Okay, we'll end there, and we will try to address this question next week on Monday. Okay, so we'll see you guys then. Have a good weekend. And yeah, we're gonna do some. We might have to do some calculus or take a Monte Carlo approach. So.